Okay, so we developed the necessary equations for solving rocket equation, and we took two cases. One is rocket in free space, and then the second case is when rocket moves under action of gravity. Now we will take up some of the problems and try to do it. Okay. So the first problem is in a rocket which moves in free space consists 80% of the fuel. Exhaust speed is 2000 meters per second, and what will be its velocity change after the first, it's a small mistake in the statement of the problem. It should be a two-stage rocket. Okay. So it's a two-stage rocket. Okay. 80% of the fuel, what will be the, right. Okay. So in order to do this problem, we have to understand the following. So we have a two-stage rocket. So this is stage 1, this is stage 2, and maybe on top we have a small payload. Anyway, so we do not worry, once again we do not worry about the how much of the payload out of this VMV, the vehicle mass, how much is payload and how much is the empty rocket cell. So what is given here is 80% of it is fuel. So MF by M0, which is beta, which is equal to 0.8. And assuming that beta remains same for two of the stages, which is, there is a slight mistake in the statement of the problem, please correct it accordingly. So it's a two-stage rocket, both of these stages have beta equal to 0.8 and beta equal to 0.8. Okay. So now we have to add, this rocket is moving in free space. So we have to use this equation, delta Vf is equal to u ln 1 by 1 minus beta. Okay. Now what happens after the first stage is exhausted? The velocity change we need to calculate. U is given as 2000 meters per second. So after the first stage is exhausted, we have a total velocity change which is given by u ln 1 by 1 minus 0.8, that is u ln 1 by 0.2, which is equivalent of saying ln 5, right. Okay. Now if we put the value of ln 5, then we already have the value of u. So we immediately know what is the value of the velocity change, right. Now after the second stage, so let us say after this first stage, it initially starts from a velocity v0 and it reaches a velocity v1. So your delta Vf is essentially v1 minus v0, right. Now it enters the second stage of burning. So what happens is after the first stage is exhausted, this part will be thrown out of the rocket and the second stage will fire. So as a consequence, the velocity will keep increasing, and because it is in, as it is in free space, we are assuming there is no maneuver in the space. So it will keep moving in the same direction, okay, along this same line. Now if the velocity changes from v, so please remember that it enters stage 2, it enters stage 2 with an initial velocity of v1. It enters stage 1, we are assuming that the initial velocity of stage 1 was v0, and now it is entering stage 2 with a velocity v1. So your delta v, I call it delta v1, which is this, your delta vf2 will be v2 minus v1. v2 is the final velocity after this stage, okay, which will be given as once again u ln 5, because all the parameter is the same. Even for the second stage we have beta equal to 0.8. So, it does not matter whether we have a stage previously or not, it will give you the same velocity change. So, the total velocity change after second stage is delta Vf final, or I will call it delta Vf total, which is given as V2 minus V0. Before the burning of the first stage started, it was a velocity, it has a velocity of V0, and finally after 2 stages it ended up with a velocity of V2. Okay. So, this is, we will see immediately that this is V2 minus V1 plus V1 minus V0. Okay. Now, this is your delta Vf1, this is your delta Vf, this is your delta Vf1 and this is your delta Vf2 here. Okay. So, essentially the total velocity change is a summation of delta Vf1 and delta Vf2, and if we do that, we see that delta Vf total is equal to delta Vf1 plus delta Vf2, which is equal to 2 times u ln 5. Okay. Now, it so happened that ln 5 is equal to I think 1.6 something, yeah, 1.61 approximately. Okay. So, then we can always put this value and calculate the total change in velocity, but that is not terribly important. Calculating the numbers might not be terribly important. What is important is, if we have, instead of 2 stages, we have a 3 stage rocket. So, instead of having 2, so what I am trying to tell you is delta Vf total is n times u ln 1 by 1 minus beta in general. Here we put beta equal to 0.8 and got ln 5. That is not, again, that is not, the numbers are not terribly important. N being the number of stages. So, if we have 3 stages, we have this multiplied by 3. If we have a single stage, we have this multiplied by 1. If we have 2 stage, we have this multiplied by 2, which we have got here. Okay. So, this is how, for a rocket moving in free space, if we increase the number of stages, the velocity change will be more and more, and that will be just a linear scaling with the number of stages we have. That was the showing this was the basic objective of this problem, not calculating this final number. By the way, the final number will be, if we put the values, the 2 u ln 5 will be 6,437.7 meters per second. So, this is the final answer. So, but this is also very important to keep in mind, that if we have n number of stages, the total velocity change will be n times u ln 1 by 1 minus beta. Okay. So, we move to the next problem. So, in this problem, we see that a rocket with initial total mass of 8560 kg is to be launched vertically with exhaust speed 1170 meters per second. How much gas must be ejected per second to give the rocket an initial upward acceleration of 8.3 meters per second? So, we need to calculate the rate of change of gas. So, essentially we have to calculate dmdt in this equation. Now, if we look back, our fundamental rocket equation is m dvdt equal to minus u dmdt minus mg. Okay. Right. So, we have to, so here actually for this particular problem we do not need to rely on the final results we have calculated. We essentially have to calculate, we can do that also, the parameters are given there, but we can also start with this fundamental equation and we can get to the final answer. Now, let us see. It is given that the initial mass m0 is equal to, what is the number, 5860 kg, and also the vertical, the exhaust gas speed which is given is 1170 meters per second, and the initial acceleration which we are looking for is, initial acceleration is given as 18.3 meters per second. Now, what is this initial acceleration? This initial acceleration is essentially dvdt. So, understand this situation. We have a rocket which is standing on the ground vertically and the exhaust gas is fired at time t equal to 0. Now, what we want is, we want the rocket to immediately start moving upwards with an acceleration of 18.3 meters per second. Now, it is not very practical, because in reality generally rockets, in real world the rocket starts very slowly and then accelerates, but let us assume an hypothetical situation, maybe it is a toy model we are working with. Here we want the initial lift off acceleration to be 18.3 meters per second. So, what we can do is, please understand, this is the acceleration dvdt at t equal to 0. Okay. So, if this is the case, then what we can do is, we can substitute this number for dvdt at time t equal to 0, and also because it is only at time t equal to 0, we can substitute this, sorry, this is capital M, please excuse me for this. In rocket equation all the m's are always in capital. So, we can substitute m0 for this m, because we are calculating at time t equal to 0. So, if when we do that, we immediately see dm dt, or rather slowly, we will do it slowly so that we do not make mistakes. So, we see that dv dt is equal to minus, or rather, sorry, u dm dt is equal to minus m dv dt. We will put m0 here because we are calculating at t equal to 0, minus m0 g, okay, or dm dt is equal to m0 by u times, there is a minus sign here, okay, right. So, this minus sign is not terribly important, because we are finally calculating a number, we just want the number, and this minus sign comes because dm dt has to be negative. Okay. Now, if we put the values here, we get, so in this equation we will just put the value of dv dt which is given, g we can take g equal to 10 meters per second square, and m0 and u we already know. So, when we put these numbers in, we get dm dt to be equal to, with a minus sign, 5860 divided by 1170, 10 plus 18.3. Okay. Now, once we calculate these numbers, yeah, so this will be, if we do this final, let us do the final calculation. oops, yeah, the calculator has come. So, we can always do this final calculation. It will be 5860 divided by 1170, okay, multiplied by 28.3. So, it is 141.74. Okay. So, our final answer is 141.74 kg per second. Okay. So, this is the final answer we are looking for, and if the exhaust gas starts at or if we have a mass, the initial exhaust rate to be 141.7 kgs per second, then the rocket will lift off with an initial acceleration of 18.3 meters. Now, in case if you are wondering if we in what happens in real rocket, if we just try to lift it, lift our rocket slowly enough, almost zero acceleration. So, what happens is at the time of lift off, dVdt becomes 0. Now, if dVdt becomes 0, we can also calculate what is the required exhaust rate to have we need for that. So, we just simply put dVdt equal to 0 in this equation. So, your dmdt in that case, when the rocket is leaving with 0 relative velocity with the ground, will be minus 5860 by 1170 into 10 kg per second, and if you recall this was almost 5. So, it will be approximately 50 kg per second. So, you see if the rocket starts exhausting at 50 kgs per second, it lifts up at 0 relative velocity or 0 relative acceleration to the ground, whereas if it starts with the exhaust with 141.7 kgs per second, then it shoots up with an initial acceleration of 18.3 meters per second, sorry, it will be second square, 18.3 meters per second square. Great. So, we move to our next problem, which will be the last problem for rocket motion and systems with variable masses in this class, but of course, you will have to solve the assignment. Okay. So, the problem is a single stage rocket starts from rest on Earth's surface. It exhausts 1/200th of its initial mass per second with a speed of 3000 meter per second and has 80% of its total mass as fuel. So, we have to calculate the total time of flight and maximum height it can achieve. Okay. So, this is a pretty straightforward calculation. Only thing is we need to first identify the important parameters like alpha and beta, and then the rest will be easy. Okay. And also u is given. So, what is given here is alpha equal to 1 by 200, beta equal to 0.8. These are given in the statement of the problem, okay, and u equal to 3000 meters per second. Okay, right. That's all we need. Now, calculation of total time of flight is pretty straightforward, because Tf, if we recall, is simply beta by alpha. So, it will be 0.8 into 200 seconds. So, the unit of alpha, if you understand, is second inverse. Okay. So, it is kg per second inverse typically when we are calculating dmdt, but please recall that dmdt is given as minus alpha m0. So, m0 is the unit of kg. So, it will be kg per second inverse. So, alpha unit of alpha is second inverse, and beta is a dimensionless quantity because it is a ratio of two masses. So, Tf is beta by alpha, which is given by this, which is equal to 160 seconds. Now, we can also calculate the, and it is moving. So, this is the time of flight. So, this has nothing to do with whether the rocket is moving in gravity or in the influence of gravity, or it is moving in the free space, does not matter really, because it has nothing to do with those. It is purely this amount of fuel and the exhaust rate of exhaust that determines Tf. Okay. Now, the next quantity we have to calculate is Zf, the maximum distance it can, or maximum height it can achieve. Now, in order to do that, we recall that the expression for Zf is beta by alpha times, okay, beta by alpha happen to be exactly equal to Tf. So, what I can do is we can put Tf here, okay, and multiply this equal to u minus half g, again beta by alpha we have, okay, we will just keep it as beta by alpha plus u by beta 1 minus beta ln 1 minus beta. Okay. So, we will once again replace this beta by alpha with Tf, right, no something is right. No, this is correct. Okay. So, we put the numbers, we have 160 outside, u is given as 3000 meters per second. So, we have 3000 minus half g we take as 10 into 160 plus u by beta, u is 3000 by 0.8, 0.8, and 1 minus beta is simply 0.2 ln 0.2. Okay. And in order to calculate this, we just need a calculator as before. We have to go to this scientific view, right. So, let us start with the calculation of 0.2 ln, which is a negative number, and we multiply this whole thing with 0.2 and we multiply it by 3000, we take divide it by 0.8, which will give minus 1027. Okay. So, once we go back here, it is 160. So, this is 5. So, it is 3000 minus 800 minus 12, approximately 1207. So, there is a point, but I am just not considering that. So, it is 160 into, so 3000 minus 800 is 2200, 2200 minus 1207. So, it is essentially plus 2200. So, it is 999.92, 992.92, and this will give you 158.8. So, we can also divide, this is in meters. So, we can divide it by 1000 to get 158.86 kilometers. Okay. So, you see that the rocket which we are discussing here with this following parameter. So, we essentially need these 3 parameters to describe a rocket. We need alpha, and also in order to have a better description, if we have m0 alongside it, which is not terribly important, but we can also have m0. So, if we have all these 4 parameters, then we can get a total physical picture of a rocket. Okay. So, the final distance is 158.86 kilometers. It is also possible, I will leave it to you as an exercise, it is also possible to calculate the final velocity change or delta Vf, assuming that it starts from ground, starts from rest. We can also calculate this, we can also calculate the final velocity. Okay, that is I am leaving on to you as an exercise. And so, we see the time of flight is 160 and this is 158.86 kilometers. But I would like to add something before we conclude this section, that probably you will get some problems in your assignment, which will show you clearly that escape velocity, which is 11.2 kilometers per second on Earth's surface, which is, do not confuse it with Vf. So, V escape is 11.2 kilometers per second, which is something close to 40,000 meters per second. It is very difficult to achieve this with a rocket which has a mass propelled mass ratio of 0.8 or 0.9. So, it can be shown by a simple calculation that if we just take this as the V final and try to put these numbers in the rocket equation with the final rocket expression for velocity with gravity, and you will see that if you back calculate the propelled mass fraction beta, you will see that it will be almost 99%. So, in order to gain escape velocity with a single stage rocket, it is important to have, it is necessary to have 99% of the total rocket mass as fuel, which is technically impossible. So, you cannot fly with 1% of payload and vehicle mass. So, that is why it is important to use two stage rockets, which are slightly advanced topic because the calculation is slightly complicated. So, I have not included in this section, but I can assure you that single stage rocket for all practical purposes is not of good use. Anyway, it is important to understand the basics of rocket equation and how to solve this rocket equation to get the final expression for velocity and final height and time of flight. So, these are although very simplistic expression, this gives us a very good overall idea of the field of rocket science, and probably you have heard the term rocket science many a times when we refer to something extremely difficult. But now I can assure you that with the board work I did, with the discussion we had in the class, that rocket science, well, it is difficult definitely, but at least at the basic level it is not that difficult. We can tackle it ourselves. Thank you.